Okay, here we are on exam 2, technically homework 5. So we're first going to start off by importing numpy as np. So we can do that by typing import numpy as np. And then the next line of code that we are going to do is, since we are going to need the root function, we're going to have to type out import Newton root. So that'll look like from scipy.optimize import Newton, comma root. All right, go ahead, shift enter. All right, yeah, I didn't think I was going to mess that part up. So now we just need to start by defining our variables, just a couple of them. So g, which is going to be our acceleration due to gravity, that'll be 9.1 as it always is. Next is our rho, and our rho is our density, and in this case it's going to be 1 e to the 3. So next we need our mu. Mu is going to be the viscosity, and for this problem our viscosity is going to be a little similar to the rho, it's just except instead of a positive exponent it will be negative. Lastly, we have our d, which is the diameter, and that is going to be 0.1, sorry, not lastly, ed. Oop. Ed is the last part, and that is the relative roughness. And in our case, that is going to be 1 e to the negative 3, very similar to the mu. So we'll shift enter on that. All right, and that looks good. We will move on to the next part. Okay, so now that we have our variables defined, or at least some of them, we can now move on to using the Churchill correlation, and this will help us find or calculate the friction factors of A and B. So we'll first start off by creating a function, and it'll be calling in RE, which is our Reynolds number, and then our ED. So the next line we are going to be using to calculate A. And we can do that by typing 2.457, and that is going to be multiplied by the log, which is np.log of, and we got a little big thing coming up here, 1 divided by, in double parentheses here, 7, and that is going to be divided then by our Reynolds number. Okay, and a lot of parentheses, we got to make sure we're staying in the right place, and that is going to be to the power, which can be denoted by using two of the multiplication symbols of 0.9 plus 0.27 multiplied by our roughness. And lastly, that's going to be to the power of 16. So next we can calculate our B, and our B is going to be a lot simpler than our A. It is just going to be 37,530 divided by our Reynolds number. And then finally, we got a return statement, and what we are returning is 2 times 8 divided by our Reynolds number, and that is to the power of 12. And then that is being added to 1 divided by A plus B. This is the Churchill part of the function, or yeah, of our function that we are doing. A to B, and that is going to be to the power of 1.5. Close the parentheses there, and then that is also going to be to the power of 1 divided by 12. So we'll go ahead, shift enter. Okay. C. Colon or semicolon, I forget the name. Shift enter one more time. Perfect. There we go. All right, now we move on. Okay, so now that we've done the Churchill part, we are given a flow rate Q, and we are able to calculate the delta head by using the head at the to node being subtracted by the head at the from node. So we can create a function, we'll call it d head, and then the variables that we are going to be using are Q, L, K, D, and then E, D. All right, can't forget the colon or semicolon. I don't know why I can't think of the name right now. So the next line that we're going to be working with is the velocity, and this is just so that we make sure we don't end up with a negative Reynolds number. So as you can see, after I type out v equals np.abs, the absolute value is what's going to make it so that we don't get that negative value. We are looking for a positive one. And then it is going to be our flow rate divided by the diameter of our pipe. So we have np.pi for pi 3.14 instead of typing out all those little separate numbers. And then this is going to be to the power of 2 divided by 4. So we can, end parentheses there. Hold up, I need some parentheses there as well. And there we can finish off with our parentheses. Okay, so next we're going to calculate our Reynolds number, and that is going to be rho, and then it is going to be multiplied by the velocity, which was just typed out before, and it's going to be multiplied by the diameter, finally divided by our mu. And now we can write a return function that will incorporate it properly back into our flow. So we are returning negative np dot sine. This is just to help make sure that it is the positive value and we don't have any weird negatives messing up our problem. And this is going to be multiplied by k, which is added to 4, multiplied by f, the function that we had just created in the last section right up here. So we do our RE and then our EB. Capitalize the D just to make sure that the signs and everything stay fine. This is being multiplied by L divided by our diameter, and then finally we are multiplying it by the velocity, which is to the power of 2 divided by 2, and that's finally being divided by g, our acceleration due to gravity. So we'll shift enter, no issues. All right, now we move to the next part. Okay, so now that we've calculated the Reynolds number, the next step in this problem is going to be calculating the flow rate. So we can do this by starting off by creating a function, flow for flow rate, and because we've already used d head, we're going to change this to a delta head. So we have delta head, and then the other variables we're going to be looking at is L, K, D, and then finally E. Oh jeez. ED. All right. Put the colon there. All right. So now we are just going to take the absolute value of this because we want to make sure that there is no negative in the Reynolds number, kind of similar to what we did in the previous step. So we are going to do DH underscore ABS, and then we are going to set that equal to NP.ABS, and then we'll do that with our delta head. All right. And then now we'll create an if statement. If our delta head, our DH, the absolute value of our DH is less than 1 e to the negative 10. 1 e to the negative 10. Okay. And then finally, we have to return 0.0. This is just because because the delta head is extremely small. So let's make sure it works. All right, cool. Now we will move on to the guessing part. Okay, so the next thing we need to do is give an initial guess for our flow rate. And a good guess that we can do is 0.01 for the fanning friction factor. So we'll title our guess Q guess because Q is flow rate and that's what we're guessing. And that is going to be equal to NP for numpy pi, np dot pi, and that is then going to be multiplied by our diameter to the power of 2 divided by 4, and then that is going to then be multiplied by np dot square root of our delta head absolute value. And then lastly, it is going to be divided by our k, and then plus 4, and this is where we multiply our guess, so the 0.01, like I said. So we can go ahead and put that in there. And then lastly, multiplying by L, dividing by D. Okay, we'll close that parenthesis. Then it's being multiplied by 2, and then finally multiplied by G. Okay. So now we can calculate the delta head based on the iterated flow rate Q, which must be equal to the delta head. So we can do that by creating another function. This one is inside of the function, and it's f to 0 Q. And what we will be returning is our d head with the variables included Q, L, K, D, and then ED. And then this is going to be subtracted from the delta head absolute value. Okay, that was weird. So next we can type resulting underscore flow, because this is the resulting flow rate that we are going to get after it's been calculated. It is equal to Newton of our f to 0 function. So we can, and the guess, so we can do that real quick. F to 0, and then also our Q guess. All right, and then lastly, we're just going to return this final return just corrects our the directionality of the delta head. So we can do that by np sine, and then our new delta head on the inside, and that is being multiplied by the resulting flow rate. Okay, let's shift enter, make sure we don't have any errors, and I am not seeing any. All right, so now we move on. Okay, so our next step is going to be adding in the array, the array right here that was provided, so for the problem. So we can go ahead, and I'm just gonna keep the similar notation that you had. We'll do pipes equals, but then we have to do np.array so that it knows it's an array. I don't think that was in, that was not in the example. Okay. And then now we can have fun typing out these long arrays. So our first one is going to be 0, comma 1, comma 1.5, comma 1.5. Close that off there. All right, and now our next one is going to be 0, comma 2, comma 2, comma 2. Close that bracket. Now we start a new one. The third one is going to be 1, comma 2, comma 1.5, and then comma 0. All right, now our fourth one is going to be 1, comma 3, comma 1.5, and then lastly 0. And the fifth one, we only have 2 more, don't worry. The fifth one is going to be 2, comma 4, comma 0.5, comma 0. And the last one is going to be 3, comma 4, comma 3, comma 2. Go ahead, close off our brackets and add our parentheses. We'll give it a quick Shift Enter. Okay, that's looking good. Alright, and now we move on to the next part. Okay, so now that we have our array typed out, we're just going to add a little bit of extra lines of code to help kind of support it and have it make a little more sense. So first line, we are going to do z equals np.array. And then in this array, we are going to have our 30 because that defines the node at 0, which has a z value of 30. So then for the rest of the numbers in here, it's just going to be zeros. I think 4. Yeah. Okay. So then we can close that bracket. All right. So now we need to input the internal pressure, particularly the node with 20,000 pascals, 200,000 pascals. Okay. So we can go ahead and do that by doing external P for the external pressure is equal to np.array. And then in this array, we are going to have our 2e to the 5, which is our 200,000. And then we're just going to have 0. Bracket. Okay. Next line, this is going to be for the external nodes. This one's a little simpler. We're just giving it a value of 0 to 4. We do not have to make an array or anything for that. And then now we can move on to our from nodes. So we'll go ahead and create a new name for that, and that is going to be equal to the pipes. Got a bracket here, semicolon, and then we'll do comma 0. Finish that, and then this is going to be a dot as type mp dot int and then 32. All right, so now we can do our 2 nodes, and then this is going to be pretty similar. There's just some like slight variations in what we are typing. So instead of a 0 like we have right here, it's going to be a 1, but the as type is going to be exactly the same. I'm misclicking everything. Pipes, start our bracket, got our colon, 1, finish the bracket, close it off, and then dot as type, np dot int 32. All right. And then now we are going to create something for the lengths of the pipe. So we can do pipes, and then we'll do bracket, comma 2. All right, and then for our last one, we're finally giving our, not L, K a value, and that is going to be equal to pipes, bracket, semicolon, and then 3 for this one. We're all just assigning different values for these. So now, hold on, let me get a little bit of water. So now we're going to need to write a little bit of code that's going to help us define the amount of, define the number of pipes that we will be working with. So we can do this by going npipes, and we'll set this equal to pipes, dot shape, 0. Our next line is going to be pipe D for the diameter, and this is going to be equal to np.full, n pipes thing we just made, and then we also have our diameter in here as well. And the last line that'll help us determine the number of pipes is going to be pipe underscore ed, and this is going to be similar to the previous line that we just typed as well, except we're just replacing the D with our ED. Go ahead and Shift Enter on this. Okay, everything's still looking good, so now we can move on. Okay, so now that we have some code written out to calculate the number of pipes we need, the next thing we will do is make some that defines the number of nodes we need. And subsequently, it will give us the exact amount of pipes that we are going to use. So we can start off this line by n nodes, and this is equal to np dot max, and then we'll do the pipes. Like we were just mentioning up before here. So this pipe is going to be the two nodes. So after we have that typed out, we can go ahead and close off our parentheses. And then this will be also a dot as type, and then same as the last part with the nodes, it'll be np.int32. But we also have to add 1 because the indexing starts at 0, so that'll help make it look a little better. So now we can do heads equals np.zeros, and then we'll call back our n nodes. And then finally, the last line will be heads. And then we have our external nodes. And then that is going to be set equal to the external pressure, which we denoted as external P. And then that's going to be divided by our rho and G as well. And then it's going to be added to our Z value that we calculated earlier. Of the external nodes. Struggling to type here, do not know why. So we can close the bracket off there. We'll give it a shift enter. Okay, no errors, so now we can move on. So next we are going to calculate the internal nodes, and this is done by using a list of the end nodes and external nodes. So like I said, we're calculating the internal nodes. New variable, and then we use the list, and then we set it, and then we have our range of the end nodes, and then this is being subtracted, like I said earlier, from the external nodes. Okay, so we can go ahead and shift enter this line. All right, no errors. And now we will move on to the next part. Okay, so now that we know the internal flow of our system, next we are going to write some code that will allow us to calculate the flows of each pipe from the iterated value to the nodes. So we can start off by creating a function, and we'll call it calc flows, because we're trying to calculate the flows of the pipes. Heads. Alright, so then our flows are going to be equal to np.zeros, and then the n pipes, our number of pipes. Okay, yeah, and then so we're going to create a for statement. So for I, in range of the n pipes, finish that off there. Our delta head, our new delta head, not the old one, not the D head, the delta head, is equal to the heads of the two nodes. So not like two nodes, but the word two. Two nodes, and then we can go ahead and put the I in there so that the for statement makes more sense. And then that is all being subtracted by the heads of the from nodes. And then same thing, we'll go ahead and put the I in there. Close that off. Alright, so now we can calculate our flows. So we'll do flows I, because of the for statement, and that is going to be equal to the flow of the delta head, lengths of I, K, bringing back K of I, the pipe, the pipe diameter with respect with I. And then lastly, don't actually type out and, the pipe of D. Okay, and then after all this, we are going to want to return our flows. So we have our flows. All right, so now we can move on. Now that we found the flows of each pipe, we can now find the internal and external flow rates for each of the nodes that we have. So to do this, we're going to create another function, and this one we will name calc, obviously, because we're calculating, and it is the net flow, which is what we're looking for. And this is making sure that we keep the flows in mind. So our net Q, which is the net flow rate, that is equal to np.zeros of our n nodes for the amount of nodes that we have. Next line is np.add.at, and we're just adding in our net Q, our 2 nodes, and lastly the flows, which we calculated in the section right up here. Getting close to the end of this one, so it'll be np.add at the exact same thing, but now we have to do it for the from nodes. So it'll look very similar. The only difference is obviously we're doing from nodes, but the flows are going to be negative. So that is something important to keep in mind. And then finally, we will just return our net Q. So we can shift enter. Oh, okay, no errors, so we will move on to the next part. Okay, so now that we know the flow rates for each of our nodes, the next part that we will be coding out is it'll be writing a function that will be able to find the roots of the zeros. So like I said, function, so we can start it off by doing def net Q internal, and we'll be looking at the internal pressure. So this is a new variable that we are defining. So we can or something that we need to keep in mind is that all internal nodes must have a net flow of 0. That is very important, and this is achieved by iterating the unknown internal pressure nodes. So, or internal nodes of the pressure. So that's why we're creating this function here, so it can iterate it for us and we don't have to do that all on our own. So we have internal nodes, and then this is being equaled to our internal P, which is then being divided by rho, also being divided by G, and finally it is being added to our Z value that we calculated of the internal nodes. So what we are returning is the roots of the zeros for the nodes. So we do return, and then we can call back our calc of the net flow rate, and then that is being used for calc of the flow of the heads. Go ahead and end our parentheses there, and then all with respect to internal nodes. Yeah, okay, that looks right. We'll shift enter. All right, no errors. So now we need to do a couple of different guesses. We are going to need to guess the internal head as well as the pressure. So a good guess for the internal head pressure is the average of the pressure that we already know. So that's nice. That's very helpful. So we can do internal head guess, creating a new thing here, and then it's equal to the NP of the mean. So like I said, it's the average of the pressures that we already know, average being mean, and then it is of heads. Got to make sure that's a parenthesis. Heads of, like I was talking about earlier, the external nodes. All right, and then we also need to make a guess for the pressure. So it'll calculate the internal pressure from the internal H using H equals P divided by rho times G being added to Z. Right up here. Same formula, it's just going to look a little different. So we can do our internal P guess, and that is equal to our internal head guess, since these correlate. Oh, okay, hold up. I put quest instead of guess. So let's go back. There we go. That looks a little bit better. And then, like I said, that is going to be subtracted from our Z of the internal nodes, which then, hold on. Okay. Get rid of that parenthesis. Which is then being multiplied by rho multiplied by G. So actually, we end our parenthesis right there. All right. Go ahead and shift enter on that. Make sure there are no errors, and perfect. All right. Moving on to the next part. Okay. So now that let me get to the thing. All right. So now that we have found our internal pressure from the internal pressure guess from the internal head guess, we are now able to solve for the unknown pressure in the internal nodes. So this is done by typing result equals root of our net Q, the internal net Q, and our internal P guess. So we will do result.x, and if we go ahead and run this, we run into some errors. Okay. Let's see. So it looks like says the name length isn't defined. Let me figure this out, and I will be right back. Okay, so I think I figured out what the problem was. Back when I was doing the lengths part, I just put length here instead of lengths. So let me run that real quick. And then I guess we can try this one more time, see if it works. It does. All right, cool. Glad I was able to fix that. So, I guess I'll leave that open. So, next section of code that we will be working with is to be able to find and print the flow rates through each of the pipes. So, we can do this by starting off with calculated underscore flows. And then we are going to set this equal to what we were using earlier, calc of the flows with respect to the heads. So now we can create a for statement that will generate our results for us. So for I, just keeping in with the same thing we used to, in range of, the range we'll be looking at is n pipes, the amount of pipes that we have. So that's good. And then we can just go ahead and do our print statement. It's going to be a little bit of a long one. So we print f from, we can do that. And then we have our initial of the pipes. And this is going to be I'm blanking. Oh, okay, and this is going to be from In brackets here, we have our I, 0. All right. That looks good. And then we can go ahead and put our parentheses around that. And then we will continue to move on. So now we have our 2. And this is for our int, int of our pipes. Jeez. From I to 1. And then lastly, we have our flow, and that is going to be calculated from we do calculated underscore flows, and this is just going to be I. So we can do that, and one of our parentheses here. Finish that off. All right. So if I hit Shift Enter and this works, we should get some values, and we do not. Okay. I guess same as the last time. I don't see anything sticking out readily now, so I will be right back once I figure out what my error was. Okay, so I think I figured out what my problems was. I just used parentheses when I should have been using brackets for certain things. So like right here, this, because I think it's just making this all a string, so we need to do, yeah, there we go. Okay, so we put the bracket there. That stays fine, but now this gets turned into a bracket, and it's going to be the same thing for the rest of these. Yeah, that's fine. And then our bracket, and then, ooh, okay, that looks a little weird too. So, flow, calculated flows of I. This first needs to be a bracket, and then we can end it with another bracket, and then I don't know why I have 2 of these. Alright, I think this should work now, if I'm not wrong. It does. There we go. Alright, that is we are very close to being done, so I will see you in the last part. Alright, so I figured out that I had another error as well. Right here, where it says return flows, I didn't have it like spaced out to the side so it lines up with the for statement. It was just like tabbed in. So I don't know if you noticed my numbers previously for the array and the calculated flows, because they were wrong. But since then, I went and just literally moved this out a little bit, and they are looking much better, more correct. So now for the last step of the problem, we're going to write some code that will print the node number, the elevation, pressure, and the net flow for each of the nodes. So we will start this off by doing a calculated net Q, and we will set that equal to our calc of the net Q, which we did earlier, and in parentheses we will have calc underscore flows and also heads, so we can end that off there. Alright, and now we just need the pressure, so we can do pressure is equal to np dot zeros, and this will be for n, the amount of nodes. Pressure of the external nodes, that is going to be equal to our external P, our external pressure. Enter, okay. And we also have the pressure of our internal nodes. And that is going to be equal to our result.x, our little array that we found here earlier. So finally, we can create a for statement for I in the range of and nodes, the amount that we have. We want to print our final values, so we will do print, and then we will do f node I. Or hold on, I think this needs to be in. Yes, I think that's correct. Like the reason I got it wrong last time. And this will also be, we will have, like I said, the elevation, the pressure, and the flow. So our pressure is going to be equal to our pressure up here, which we just wrote out a little bit of code for, of I, because of the different iterations that we have. And then we can go ahead and close off the brackets there. And then we have our Z, which is denoted by, we calculated it a little bit of a while ago. So we have our Z, and then finally our net flow. So I guess not next, we can do net Q, and that will be for our calculated underscore net Q of, in our brackets, we have I, and then we can close off with that. All right, let's run it, see if it works. And it's looking like it does. All right, well, thank you very much for watching this video, and I will see you in the next one. Goodbye.